Mr. Tarou, in this math lesson we are going to be defining and comparing the ideas of union and intersection of sets. This will be in an algebra book. You could be just in the very beginning of a probabilities class. You're also going to see this concept come up. I'm sure there's other examples, but I touch on this when I start going over probabilities in my AP statistics class. So it comes up quite a bit, and hopefully you find this helpful. Within this lesson, we are going to be defining union and intersection. We're going to be looking at how Venn diagrams can help us answer questions on this concept. We are going to be defining and discussing the idea of disjoint or mutually exclusive events, whatever vocabulary word your textbooks happen to use. And then we're going to do two examples. The first example is going to have two events in it, and we're going to answer quite a few questions based off the Venn diagram that we developed from that first setting. And we are going to, within that example, be discussing the idea of complementary events. We'll finish up by setting up a Venn diagram for a situation where there are three events. We're just going to basically ask a question. There's three possible answers, and make a Venn diagram that represents that situation where there are three events. It's a bit more complicated than when there's just two. And if you're in an algebra book, most of your problems, will be just dealing with two events at one time. The union of two or more sets is the set that contains all elements of that set. That sounds very mathy, but hopefully we clarify what that means as we go through our first example here on our board. The symbol of union, which just looks like a capital U, sort of like a cup that can hold all of the elements, is red or. So this is red or as you're looking at your problem. So A or B. Okay. For an element to be in a union, a new set created by this idea of union, it needs to be an element in one or multiple individual sets being considered. So again, this is all very mathy. Let's see what it looks like in practice. It's pretty simple. We have, well, at least this example is going to be, we have set A, which has the elements in it of 1, 2, 3, and 4. And we have set B, which in it has the elements of 2, 4, 6, and 8. Now, if I wanted to, look at the answer of what is in A or B, I'm pausing because I'm thinking, well, why did I write the answers already in this problem? But we'll actually work through some examples here in the next screen. So what elements are in A or B? So I want you to list, as it states here, all of the elements that it's in one of, or in this case, both of the sets. Now don't repeat the numbers. That's going to be incorrect. Just list off all the values, all the elements that are in one or both of these sets. So we have 1, 2, 3, 4, so they're listed right here. Now we have 2 again, but you'll notice when I wrote this set representing the union of A and B, I do not repeat that value of 2. I've already written it. Then we have 4, that was already in there as well, and then finally 6 and 8. So A or B is the set which contains the elements of 1, 2, 3, 4, 6, and 8. And just mentally in your head, when you see A or B, you're asking yourself again, what are the elements that are in, well, A or B? Okay. Over here we have an intersection. Well, the intersection of two or more sets is the set of elements that are in all of the sets. If, again, you are in an algebra book, it'll appear like all your problems only have two sets. So you'd be probably thinking that the intersection is the set of elements that are in both of the sets. But if you have more than two sets, you want to change that language to all of them. So the symbol for intersection is that U turned upside down. I like to think of it as if you turn a cup over, how much water could you put in the cup? Well, you can't fill it up completely. It's just a little bit of, I guess kind of whatever water is held with that cup turned upside down, probably based by surface tension or something like that. The point is, when that cup is turned upside down, it can't hold as much. And that's what you have as far as comparing the idea of union and intersection. For a union to, for an element to be in a union, it has to be an element in one or multiple individual sets to be considered, but getting back to reading the definition, the intersection of two or more sets is the set of elements that are in all of the sets. So that's not going to be as many values. So usually, so we have A and B. You know, what elements are in both, because this is intersection A and B. And I'm using the same example. Well, we have 1 is only in set A. The 2 is in both of these sets. 3 is only in set element, or the element of 3 is only in set A. The element of 4 is in both of these sets. And then finally 6 and 8, those elements are only in set B. Now, we listed all those values for a union, but when we're talking about an intersection now, A and B, that's only those values that are in both of, or elements that are in both of those sets. So the answer is 2, 4, and notice that I did not write each of those values twice. Now, a Venn diagram for the setting. A Venn diagram, you're not going to see it in this example. We'll discuss it as we continue through our lesson. The rectangle is actually 100% of all of the elements that are being considered for that particular problem, not the circles that represent the individual sets. So, or events if you're talking about a word problem. So event A, or set A, I'm saying event because of you know, the questions that I do in AP statistics that are always applied to real word problems. But set A had those values of 1, 2, 3, and 4. So I have a circle which is going to contain those 4 elements of 1, 2, 3, 4. I have a circle which represents set B. And in set B, I have the values of 2, 4, 6, and 8. Now, when you set up a Venn diagram, not only do you need to remember that that rectangle represents 100% of all of the data or elements that ultimately could be considered in your problem, but as you start to fill it out, you want to do the overlapped area first. So as I look at set A and set B, I want to focus on that intersection. What elements are in both A and B? And we want to fill out those values first. So we have 2 and 4. 2 and 4 are both in the circle representing set A, and they're both in the circle representing set B. And that's why our union, you know, is the values of 2 and 4. Now, this circle is supposed to represent all of the set A, and so we need to go in here in a part or portion of this circle that is part of A but not in part of B, and fill in those values of 1 and 3. And then finally 6 and 8, same idea, filling up set B. And this Venn diagram now represents each of these two sets. Now for the shading, let's see here. Let's do just purple here for the shading of the union of set A and B, or A or B. And shading that in, this portion of the Venn diagram represents that union notation. And might seem overly simplified in this particular setting, but Venn diagrams can be very, very helpful for working with these union and set notation problems, especially in statistics, and I'll point that out as we continue through our questions today. And the portion of this Venn diagram that represents, let's see, a nice bright color, hopefully that will stand out. We'll do blue. Blue is actually probably too close to purple. How about green? Hopefully that sets up. If I want to shade the portion of this Venn diagram that represents the intersection of set A and B, where we're only considering elements that are in both of those groups, that's the overlap area. So you're probably not going to be able to read these letters or these numbers very well now, but this overlap portion where the circles that represent these sets overlap, that is representing the intersection of set A and B. So we got this first page of notes done. Let's get on to defining what disjoint or mutually exclusive events are. Bang! Disjoint or mutually exclusive events share no common elements. So, as an example, we have set A with the elements of 1, 3, 7, and 8. We have set B with the elements of 2, 4, and 6. So, what elements are in the intersection of A and B, or what elements are in A and B? They don't have any common elements, and so that would be an empty set. That is your indication that set A and set B, or if we're talking about application problems, event A and event B are disjoint events or mutually exclusive. Now, what elements are in the union of A and B, A or B? Well, again, of course, if we want to list off these elements, we're listing off all the elements that are in at least one of our individual sets. And don't write down the repeat numbers more than once. So we have 1, and okay, so that's 1 there. Element, we have 2, 3. Well, actually, I just looked at that. Let's just do this. 1, 3, 7, and 8. There's really no reason for these to be in order. Then you go to set B, and there's 2. That wasn't over there. 4. That wasn't over there. And 6. I'm checking this other set because I don't want to write a number down twice. Okay, let's make a Venn diagram that represents these two individual sets. We have set A and set B. We're going to go ahead and draw a circle for each of those sets. And most of the time I would have those circles overlapping because, well, a lot of sets are not disjoint or mutually exclusive. And in set A, we have the values or the elements of 1, 3, 7, and 8. And in set B, we have 2, 4, and 6. And one more time in writing, in a Venn diagram, the circles represent the individual sets, and the rectangle represents all of the data or elements that could be considered in whatever particular situation you're dealing with in that problem. Again, I keep saying that, and we'll be looking at that in our as we go through our examples. In a school of 800 students, actually right here, in a school of 800 students, two main sports are football and baseball. 65 students played football, 10 did both, and 705 students played neither sport. So while it's the two main sports, of course, most of the students in your school, I'm sure, are not playing one of these two individual sports. We want to make a Venn diagram to represent this setting because ultimately I'm going to erase the left side of this board and we're going to answer all kinds of questions based on this setting. Okay, now Venn diagram, start with your rectangle, and that rectangle is going to represent all of the students in the school. I hear a little bit of static though, so let me pause the video and change channels. Okay, hopefully that is better. Now, this rectangle is representing all of the students that attend the school, all 800 students. Now we're going to come in here and we're going to create a circle that represents set A or event A. That would be, let's say that A is going to be for students that are playing football. I guess I probably should just call that F. Let's do that. Take that out of there. This circle is F. Okay, now we're going to introduce another circle that is going to represent those students that say they play baseball. So let's call that B for baseball. And that overlap, which I probably have to redraw that to make sure it's a little bit bigger so it's legible. That overlap is going to represent students that are playing both sports. Now, when you make a Venn diagram to represent a word problem, you want to start at the most overlap where most of the sets share the same space, where there's the greatest intersection, if you will. So let's see here. We have 800 students. We have 65 play football. And you might be tempted to go, okay, football, 65. That circle is for football players. And then 10 played both. And if I put that 10 in there, now I just said you want to start with the overlap area, the intersection, and work your way out. Well, if I just say, oh, football, 65, 10, or both, add up the numbers that are in this circle representing the set football. Well, 65 and 10, that adds up to 75 players, which may not be bad for, maybe, I don't know what average high school football teams are, how many players they have, but this adds up to 75, and the problem specifically says that there's 65 students playing football. So that is why you want to start with the intersection of all of your circles first and work your way out. So we already have 10 accounted for, 10 football players accounted for of the 65. So there are, looking at what we have right now, we have 55 football players that don't play baseball, and then we have those 10 that play both. But that 10 is still in this circle representing the set of football. You have 705 students that don't play either one of these sports, and this is where I want to keep emphasizing that in a Venn diagram, the rectangle represents all of the data or all of the elements that could be possible in your particular setting. And our setting here is the 800 students that attend the school. So out here, we're going to have 705 students that don't play either one of these sports. I've put as much information as given in this Venn diagram, and I still have a portion of it that's not labeled. Well, all of these numbers have to be accounted for, and we need to ultimately have 800 students in the school. So we've got 800 minus 700 is going to be 100, and 100 take away 50 is going to be down to 50. 50 take away 10 is going to bring us down to 40. 40 take away 5 is going to bring us down to 35. And then take another 5 away and we're down to 30. So that means that there's 30 players that only play baseball. And then we have those additional 10 players that play baseball. So this circle is telling us that it looks like we have 40 students playing baseball. 10 of those, also play football. Now, just to make sure this is right, do these numbers add up to 800 like the problem states? So 700, 750, 760, 790, 795, and 800. So now my Venn diagram, I have all the portions filled out that I can, and all of these individual parts add up to 800. Okay, so now we've got our Venn diagram set up. We're going to do a couple of things here. I'm going to step off, erase the board, put a bunch more examples up here, and then we're also going to be defining the idea of complementary events and use that new definition and symbol to go along with it to label the different portions of this Venn diagram using set notation, the and or symbols, along with our symbol that stands for complement, which you don't even know what that means yet. Bam! How many students play baseball? Part B of our example. I didn't really mean to, but we've already answered that question as we were setting up the Venn diagram for this setting. We have those 30 students that are playing baseball only. We have the 10 students that are playing baseball but are also playing football. Well, with the Venn diagram, the nice thing once you have these set up is you just count the parts that fit that particular question. So 10 plus 30 is equal to 40 students. Excellent. How many students only play football? Okay. Not how many students play football. That would be a total of 65. That was given to us in our problem. But only play football, well, that's going to be the 55. That's going to be the students that are in the football circle that are not in the baseball circle. That represents that setting or that set. So that's going to be 55 students. How many students do not play baseball? How many students do not play baseball? Well, these 55 students that are playing football, they're not playing baseball. They're playing football and not playing baseball. But there's also the 705 students in the school that are not playing either one of these sports. They might be doing golf or tennis or basketball or something that's not related to this problem or no sport at all. But the part of this Venn diagram that is not in the circle representing the set of baseball players is 55 plus 705. So 55 plus 705 is going to be 760 students. And now we have this idea. I told you we were going to be defining what complementary events are. And I've already sort of used the language of complement, but we need to define it, and there's a notation for it in case you might see that in some of your questions. If A is an event within the sample space S, and so for this particular setting, our sample space is going to be the students either play baseball, they play football, or they play neither. I'm not considering any of the other sports that are offered at the school, or even, whether it's raining or snowing, as a weather event. So A is within the sample space of S. The complement of A consists of all elements, all the outcomes, again, that's sort of like language for word problems, in S that are not in A. And the notation for this is sort of A with a little dash. Now, if you're in calculus, that means derivative, and if you're just in English, this is some kind of ownership type notation, like Rob's car. But at any rate, we have A prime, or whatever your textbook may be calling that symbol. We have A with a little exponent of a C, and that's where the complement of A. This is the notation that my AP Statistics book uses, that I teach out of. And this notation is in my algebra book, and, well, not my algebra book, but the one I'm teaching out of. And then this little squiggly line in front of the A. Now, I'm not exactly sure what to call this notation either. This notation is not in the algebra book that I teach from. It's not in the AP Statistics book that I teach from, but I have seen this notation. But at any rate, I had to go look up that symbol. Actually, I had to look at the key to make sure I understood what exactly they were asking. So all three of these symbols, and hopefully there's not more, are used to denote the idea of complement. Okay, so the complement of A consists of all elements or outcomes in that sample space S that are not in A. Not in A. Where did I hear that language before? How many students do not play baseball? The complement of playing baseball, that was the 40 students that played baseball, is to say we're not playing baseball. In this setting, the complement of playing baseball is not playing football, because you don't have to be playing a sport at all. And if I opened up to even maybe, I'm not going to try and list all the sports that my school has, but, not playing baseball is not playing football, or playing basketball, or baseball, or tennis, or golf, or swimming, or track, or whatever, wrestling. It's just that language of, I don't care what you play, or even if you don't play a sport at all, how many students are not playing baseball. So now the notation for that, this answer is, B with a little dash on it. That is going to represent the complement of B. How many students do not play baseball? 750. Or you might see that as whatever letter we're indicating the set of baseball with. B with a exponent, if you will, notation of C, or this little squiggly line of B. Chalk down! And the answer to either one of these questions is the 760. These are all notations for not playing baseball, the complement of playing baseball. Now that we have the idea, the definition of complements, and we have this new notation to play with, I want to fill in this Venn diagram with some of that set notation we talked about earlier in the video, and now this idea of notation. I'm going to use this upper exponent notation of C and label the different parts of our Venn diagram with a color that I haven't used yet. So let's use orange. This overlap, these 10 players are the players that are involved in both football and baseball. So that's the intersection of those two sports. So this center area right here is football and baseball. Now, we talked about these 55 students playing football, but also not, and they're not within the baseball circle. So this portion of our Venn diagram is going to be football and not baseball. That's a little C right there if it's not very legible. This portion, the 30 students, those are the students that are playing baseball and they're not playing football. In this Venn diagram, the rectangle is the entire sample space. The 705 students, they're not playing football. They're not in that football circle, so they're sort of the complement of F, if you will. And they're not in the baseball circle, so they're not playing football and they're not playing baseball. And so there's some set notation, well actually I don't have any unions in here, but I have some intersection notation in this Venn diagram to help you with that as well if you happen to see that in your textbook. Bam! Bam! Our last example, so sad. How many elements are in? Now we have a Venn diagram that obviously has three events or three sets in them, set A, B, and C. We don't have to set this up, we just have to answer a series of questions based on this Venn diagram. So how many elements, each one of these numbers represents the number of elements that are in that set, are in A, and in B, and in C? Well, with intersection, of course, for a element to be considered a solution or part of that intersection set, it needs to be in all of these. So that's going to be where the set of A, B, and C overlap. And that is right dead in the center, and it is equal to 25 elements. How many elements are in A and B? And now I'm going to use all three different, actually I didn't use all three different notations here, did I? Let's change this to C with a little exponent on it. So I'm using all three notations that, at least that I know of, that you might see for complement. A and B, and not in C. A and B. Okay, so here's A and B, and I want the elements that are in A and B. I started moving my hand over all of this, but it's not or, it's and. So that's again going to be the overlap. So 40 and 45, that's the number of elements that are in both A and B, as this intersection notation, is asking for. But and not in C means that I don't want to include this 25, so the answer is equal to 40. There's 40 elements that are in set A and in set B and not in C. How many elements are in A and not B and not C? So here are all of my values representing the number of elements that are in set A, and I don't want them in B, so I don't want to include that 40, and I don't want them in C, that notation for complement again, and so my Venn diagram, the only part that's left, the part that is A and not B and not C, is the 190. How many elements are in A? Now this is or B. Now when we do this work in my AP statistics class, I give them from the book probability rules, and there is a sort of a rule for this idea of or, this union, which is an addition rule for disjoint events, those mutually exclusive events that do not occur together. And it just says the probability, we're not really doing probabilities here, but the probability of A or B is the probability of A plus the probability of B. Basically, you just add them up. But then I have to give them an additional rule, which says the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. See, without a Venn diagram, and again, we're just looking at Venn diagrams, but thinking about word problems and things that you'll run into later, this idea of or, the overlap gets counted twice. You know, how many elements are in A? We've got 190, 40, 25, and 50. So whatever that adds up to, that's the number of elements that are in set A. How many are in B? Well, B is 130, 40, 25, and 80. How many elements are in A or B? Well, if I just took all of these values and added them up and said, okay, I don't know, that's how many numbers are in, or elements are in set A. This is how many elements are in set B. Wait a minute, I just included the 40 and the 25 with set A, and I'm including these 40 and 25 elements with set B. They're getting counted twice. So you have to subtract out that overlap area, because without a Venn diagram, with that as a visual aid, you're going to count those twice, and so you have to subtract it, not because you don't want the overlap area, because you don't want to double count. So with a Venn diagram, we don't have to worry about that. How many elements are in A or B? You know, and for an element to be considered sort of a part of this union set, it needs to be an A or B or both, but don't count the both twice. So we have 190, we have 50, we have 25 and 40. We've got the 80 and an additional 130. And right off the top of my head, I could add those up, but this video is already running a little bit long. That is going to be 515 elements that are included in set A or B, the union, of those two sets. Now finally, we have a little bit more complicated of a problem. We have some parentheses, and please excuse my dear Aunt Sally, you got to do those parentheses first. How many elements are not in C and B? Okay, so I don't want to B and C at all, but I need to include the number of elements that are in B, the intersection of not C and B. Well, this is B, but 25 and 80 are in the circle representing set C, so I don't want to include those. So I'm looking at 40 and 130. Or, okay, right? Now we're talking about intersection and union, or A. Now for an element to be considered as part of this set, to be included in the set, it needs to be in, sort of the first set, or the second set, or in both. So now, let's see what we have there. Or A. Not C and B, took care of that, or A. Well, all of this is A. And so we're looking at 190. I don't want to include the 40 because the 40 was already counted for, that union. You don't want to count that intersection area twice. That 40 is included in the not C and B part of this problem. So I'm not going to include the 40, but everything else in A. We've got the 50. Now, in the first part of this problem, when we were working in the parentheses, I said, hey, I want the complement of C. I want the elements that are not in C. But that's only for this intersection notation that's in the parentheses. Now I'm just looking at A, and the or A does not have any conditions about not including values that are in C. So that's going to be the 50 and the 25. And again, I am not including the 40 as an element, the number of elements that are in set A, simply because we've already counted it once, and I don't want to, with this or, count the overlap twice. And we do want to add these up, and ultimately that is going to come out to be a total of 435 elements are in not C and B or A. And that is the end of my last example. I'm Mr. Taru. Go do your homework.